So, this is it.
This is a quantum computer.
This is a quantum computer.
Here I am seeing a real-life quantum computer for the very first time with my friend and king of tech YouTube, Marques Brownlee. And I'm finally understanding why quantum computers are such a big deal.
Quantum computers.
Quantum technology.
What on earth is a quantum computer?
Bits, qubits. Try all the codes at once.
Whichever nation first develops a practical quantum computer will have a tremendous advantage.
Quantum supremacy.
I see a lot of news about quantum computers, and it's always extremely confusing.
That was really well done, and I still need to rehear it.
But also, it's often wrong. Quantum computers aren't supercomputers. They aren't bigger, faster versions of what we use now. There's something totally different. And that difference is actually the key to understanding why they're such a big deal, why governments around the world are battling it out to build them the fastest. Quantum computers are wild. They're on track to change what we can build and how we understand the world. They're kept at temperatures colder than space. But if you think you really understand how they work, you're probably wrong. At least I didn't. And that's where this video starts. Marques and I both realized that there was this big, important technology that we really didn't understand. So we decided to go on an adventure to figure out the truth about quantum computers, what they can really do, and why we should care. And of course, we're taking you on that adventure with us to show you what we learn as we learn it. And more importantly, to show you how these crazy computers might actually impact your life, and sooner than you think.
It's a very niche skill we just got, which is being able to hear when a quantum computer is working.
What does it sound like?
So it works. It's not broken. I swear I'm usually good with tech, but...
Like, the only function of this screen is to provide directions. You're getting this? So we're going to visit IBM's quantum computer. This is really exciting that they're letting us see this computer because it is, to my knowledge, the largest quantum computer that exists, which I say with confidence, like I know what that means.
I was gonna say, what is biggest? Because like I heard, you know, like supercomputers, they're massive rooms full of computers, and when someone says we have the biggest supercomputer, I'm like, oh, I can picture that. The largest quantum computer, I'm not even sure what to picture.
I imagine the golden octopus. You know, that thing that Biden looked at like this?
The press images, yeah.
Yeah, and I know that in order to see that, they have to shut down the computer. So this is like, took some real logistics on their part to allow us to see it.
This is a real deal.
What is most interesting to you about quantum computing?
It's definitely on the edge of my expertise, I would say. I'm really curious about when it's actually going to touch like regular people.
Yeah,
my whole concern is purchase decisions. At some point in the future, quantum computing will come into play with a real purchase decision. Someone will have like a device that they can buy where quantum computing is a part of it, or maybe went into its creation at least. When are we going to get to that point?
One of the things that I think is very important to make clear is this is a different kind of explainer. You're just coming with us as we figure this out.
Exploratory explainer.
Exactly,
Yeah.
the whole new genre. Along for this adventure are Cody and Nicole. Nicole is an associate producer on this episode who is also studying quantum communication for her PhD. And Cody is our DP, the man behind the camera. Thank God they're both here. So, when I started doing this episode, I spoke to a really famous quantum physicist. He was really frustrated at the way that people were talking about quantum computers. And I was like, okay, how do you want people to think about them like them? Okay, here's the analogy that helps me understand what quantum computers are good for. Imagine that you're on a video game map, and how you get around depends on how good you are at doing math. You may not want to play this video game. Bear with me. So first, there were no computers. Things like geometry and astronomy took forever. So you have your little pencil and paper and you're traveling across the mathematical map by walking. So it was slow. And there were lots of areas that we just couldn't explore because it was beyond our computational ability. But then we developed early computers, and that allowed us to input larger data sets and answer problems that had previously been out of reach. These new computers unlocked new areas on our mathematical map. Instead of walking everywhere, we can now ride horses. We can get farther faster, and we can access areas that were previously inaccessible. But there were still parts of the map that our computers couldn't access. Luckily, computers just kept getting getting better, and they allowed us to solve more and more complex math problems. As a result, our virtual map has transformed. We have roads and cars, and we're just reaching areas that were previously unreachable. Better computers mean traveling across this map faster and more easily than ever.
The thing that he said was really important to understand is that quantum computers are not faster cars, they're boats.
A boat is not necessarily better than a car. They're just built for totally different terrain. So with our new quantum computers, we're beginning to navigate these new mathematical waters, solving problems and discovering areas that traditional computers just can't.
My question for IBM is, what's in the water?
Oh, wow.
What are the oceans that we're all of a sudden able to explore with our quantum computer boats?
I love this. I'm an analogy person, so I'm like fully absorbed in this now.
This is why I think a quantum computer is never going to beat an iPhone. But I think that this is a better thing to offer the audience, like to offer you guys, instead of like quantum computers are just another exciting computer.
I guess what people are probably clicking on this video thinking in their head is, will there really never ever be a quantum computer in my pocket? And I guess that would be, will there ever be a flying car boat? You know? Is the tech ever going to get to that point? It's just a question.
I just want to say I really appreciate your commitment to this
I
analogy.
love it. I love the analogy.
Guys, we have arrived. Where we have arrived to, this does not look like there's a quantum computer here. IBM Research Division. Here we go. All right. Let's go. Let's go see a quantum computer. We made it.
We're here.
Here we go.
Do you want to introduce yourself first?
Oh, sure.
Olivia, audience, Olivia.
Hi, I'm Olivia Lanes. I'm a researcher at IBM, and I also work on the education and the community team. We're gonna go look for a quantum computer.
What's going on here?
This is our Watson setup. No, please go ahead. This is like where the Watson AI thing was displayed, and it like competed on Jeopardy with like Ken Jennings.
Watson, what is issue? You are right.
This is Brent. It's Brent's lab, so it's very nice of him to
Great to meet you.
let
Thanks
us
for
in.
having us.
So this is the lab.
That's a quantum computer?
Yeah, but actually this is a dilution refrigerator. This whole thing is basically constructed to keep the quantum computer very, very cold, 15 millikelvin. It's the coldest thing basically in the universe. It's colder than outer space.
So inside that is 15 millikelvin.
Yep. So here, let me show you the one that we can like play with. This is it.
This is a quantum computer.
This is a quantum computer. The quantum computer is a chip in this one here, but this whole thing keeps the quantum computer working at insanely cold temperatures like we talked about.
So this is all refrigerator technology.
So all of these cables that you see here on the side carry signals down through the fridge into the processor, and then they do their quantum stuff, and it comes up and it goes to these room temperature control electronics, and they turn it into things that humans can understand.
That is a quantum computer. We were allowed to touch it, which was cool.
Oh my God.
So I think it's really funny that when people generally talk about like the difference between classical and quantum computers, people are like, okay, well, you know how a classical computer works, right? But like the truth is that like nobody knows that. A simplification of it is it comes down to bits. And bits are made out of pieces of silicon, and you have, you know, tens of thousands to millions of them in your computer. And they can either be in the state 0 or 1. We call it the ground state or the excited state. And everything that you type into your computer, like all words, all numbers, all colors, get translated into computer speech. But it's very binary, right? A quantum computer is run on qubits.
Qubits aren't like bits. They aren't a 1 or a 0. They're more complex. Think of this like a wave. A qubit could be really likely to be 0, which means a lower energy wave. Or it could be really likely to be 1, which means a higher energy wave. And each qubit has a probability of being each. When a quantum computer is working, the probabilities of multiple qubits interact.
And they add constructively or destructively, just like waves would. If you were to like tap like 2 places in a pond.
You know how when you like explain something to a 2-year-old and they just keep going, why? And they have to explain it again and you go, why? Yeah. My question is, as the controller of the computer, you decide what about those probabilities?
basically you are altering the probabilities while you're running an algorithm.
It's a common misconception that quantum computers try all the options. That's not right. This is simplified, but it's more like a quantum computer kind of watches the pond. It watches how all of those waves interact and then finds the most likely answer. If this is all confusing, don't worry. All you really need to know is that quantum computers calculate things very differently than classical computers do, and that makes them good at different things.
Quantum computers are not going to be faster at everything than a classical computer. Like, it's not good for addition, right? Because your calculator and your phone is perfectly good at that. But the things that quantum computers are good at is finding structure in tons of data. And if you're interested, we can close it back up.
Absolutely. Put us to work. Yeah!
Let's go back to our virtual map. So we have our boats, and we're floating around discovering new parts of this map. One of the first new areas of interest is simulating nature.
Simulation of nature seems really interesting. Why is nature one of the things?
So nature fundamentally is quantum, and it obeys quantum physics. We just don't normally see it. But if you look at like a molecular level and like the atomic structure of molecules, everything has to follow the laws of quantum physics. It's really hard to calculate what a material or what an atom is going to do past a certain size. So at a certain point, it just can't do it. But if you're interested in like developing battery technology or creating new materials that have, long chains of molecules, you're going to need a quantum computer.
This is why people are so excited. Think of the new materials or medicines or molecules that we could make if we could better predict the way that nature behaves at a molecular scale.
Oh, yeah.
Yeah.
There you go. Boom.
Okay, so simulating nature is something that quantum computers could be amazing at. But we're also getting closer to another use for quantum computing, one that people and governments are more concerned about.
Completely new encryption algorithms.
Break encryption.
Quantum-resistant encryption.
A fully functional quantum computer could be built with code-breaking capabilities that could render all forms of online encryption unreliable.
Okay, now this is the one that I've been waiting to ask about.
Okay.
Why is everybody so obsessed with talking about quantum computers and encryption?
So the first major algorithm that was developed for quantum computers is Shor's algorithm, named after Peter Shor. Super nice guy. He invented an algorithm which basically can find factors, prime factors for really large numbers. Why does anyone care about this? Because that's the basis for RSA encryption, which is basically how all transactions on the internet are conducted. And the entire reason that all of our encryption schemes today work that way is because it's basically impossible to crack that with a brute force classical algorithm. It would take, I think it's like billions of years. But a quantum computer could do that way more efficiently. We're talking hours to days.
So this global race now makes a ton of sense. Whoever gets a quantum computer to actually do this has a big, obvious advantage.
But we haven't done that yet. That's one of the ones that requires probably like 1 million qubits or more to do, but we're working up to it.
So we're not going to be using quantum computers to break all internet security right now. Today, we're at 433 qubits, the record set by IBM. 400 to 1 million qubits is a big difference, but Olivia is confident that we'll get there sooner than you think.
In the next 5 or even less years, we're going to see people switching over to quantum safe algorithms because of this reason.
So RSA goes away and we have quantum safe encryption instead?
Probably. Not all at once,
Yeah.
but gradually you're going to see people do it. We're progressing at an incredibly fast rate. We're solving problems that people didn't even begin to know how to crack 2 years ago. But we've done it. Like every single year, everything that we say we do, we do. Nothing mathematically or physically prevents it. And so if the physics says it's allowed, the engineers will find a way.
That's sick. I'm adjusting the analogy slightly, that it's submarine because there are sort of different levels of quantum computing.
Yeah. We are just skimming the surface. We're going to keep iterating and improving upon this technology every single year. And we're probably going to discover like new applications that we haven't even considered yet.
It's a bottomless ocean.
It's a bottomless ocean.
The tour was amazing, and as we left, we thought about what we learned.
Awesome. Let me just get on the highway and then I will have thoughts. Quantum computers do look exactly like I imagined they look. They look like the pictures.
Like the picture, yep.
But something about being in person with it was just like, oh, helped me understand that this is a fundamentally different technology. Like, it just looks so weird.
I'm really glad I got to finish exploring that analogy and fully understand it too, and adjust it a little bit to like really encapsulate at least everything that I currently understand about quantum computers, in that there is an evolution into the future of them, and that they are specialized and really good at certain things. Just, I like a good analogy, so that helped a lot.
Okay, so what is your summary of the analogy now?
I think we can keep almost all of it, which is that our exploration of other fields of mathematics and physics and science was equivalent to other steadily advancing forms of transportation around our imaginary video game island. But I liked adjusting to submarine because there are levels to it. It's more of a bottomless ocean in that we're just going to keep going. The tech gets better. There's no physical limit. It just continues to improve.
Here's how Olivia put the dream of how we'd actually use quantum computers.
It's beautiful because, like, of course, we all want to make the world a better place. We want to develop technology that's going to enable us to do fundamentally different and better things. But it's also beautiful because, like, part of the human experience is you just want to, like, learn what we are and, like, learn more about the world we live in. And the